chasing waterfalls.
Welcome again to today's class. So today we shall look into another important topic in chemistry, that is chemical kinetics. Yes, from the word kinetics is derived from a Greek word kinesis. Kinesis. A Greek word kinesis, which means movement. Yes. And so when you come across to this word kinetics, what comes to your mind is movement. Okay? Now, unlike thermodynamics, which talk about the feasibility of a reaction, chemical kinetics, what it does is that it discusses rates of chemical reaction. Yes. And so rate equation, when you have rate equation to be equals to k a raised to power of x b raised to power of y, where k is what? Rate constant. It means that when you add this x and this y, what you'll be getting is called the order of reaction. Order of what? Reaction. Take for instance, if you have r equals to k a raised to power of half b raised to power of 3 over 2, you tell them that x plus y, that means 1 over 2 plus 3 over 2 will be giving you 4 over 2 equals to what? 2. We call it second order. Second order reaction equation. This means second order. Then when r is equals to k a raised to power of this simple mean concentration. So when we have r equals to k a raised to power of maybe 0 and b raised to power of 1, you will notice that your x plus y will be equals to 0 plus 1 equals to 1. That is first order. Yes. Then when you also have r equals to k bracket a raised to power of, let's say, half, b raised to power of minus half, you would tell them that x plus this will be equals to half plus half minus half plus half equals to 0. We'll call this 0 order. When you also have r equals to k a raised to power of, let's say, 1, b raised to power of minus half, you tell them that x plus y will be equals to 1 minus half equals to half. This is what we call half order. So in chemistry, we have many order reactions. And it's important for you to know from this example, we can see half order, 0 order, first order or 1 order, second order or 2 order reaction. Yes, but the one we'll be discussing in full details in this video is 0 order reaction, first order reaction, and second order reaction equation. We need to check out what are the intrinsic properties in this reaction equation just mentioned. Okay, so let's go into them one after the other. 0 order reaction. 0 order reaction. For the 0 order reaction, its equation is concentration of any time equals to initial concentration minus Rate constant times what? Time. And so that is the equation for it. Okay? And so what we do here is we will check out a lot of things here. First thing we will check is the half-life. Half-life. And the next thing we will check is shelf life. Very important. This is because at elementary level, we need to understand this life we talk about, half-life, shelf life. At higher level, we talk about all the types of half-life, biological half-life, effective half-life, and all have you. But at elementary level, we want to just talk about the physical half-life of this. Yes, we'll discuss them in details now. So, if the one we are talking about is physical half-life, for instance, it means the time it will take that element to decay to its half physically, the time it will take that element to decay to its half physically, or the time it will take 50% of that element to decay physically. You get it? And so that is about physical half-life. Then when you talk about biological half-life means the time it will take 50% of that drug or of that substance taken into the body to get eliminated. The time it will take 50% or half of that substance being ingested into the body to get eliminated from the body. And when we talk about elimination, elimination simply means metabolism and excretion. So two things make up elimination. When you talk about elimination, so to speak, it means metabolism and excretion. So the time it will take 50% or half of that substance to get eliminated from the body is called biological half-life. But if it is not happening in the body, if it is happening physically, the time it will take 50% of that substance to get to decay to its to decay. The time it will take 50% of that substance to decay is called physical half-life. But if it's taking place inside the body, you call it biological half-life. That is the time it will take 50% of that substance to get eliminated from the body. So you have to take note of these points. Okay? Now we are taking the physical half-life first. So the time it takes 50% to what get eliminated or to get decayed is what we check. That means our C will be equal to 0.5 CO. 50% means 50 over 100, that is 0.5. You put it here. You will be having 0.5 CO equals to CO minus KT, 50%. And so minusing, you now say this is 0.5 CO minus CO equals to minus KT. 50% means half, like 50 over 100. This minus this minus 0.5 CO equals to minus KT half. And so T half, which is the half-life of a zero order reaction, is minus 0.5 CO all over minus K, where the K is talking about K0 order. And so minus will cancel this, right? And it's giving you CO all over what? 2. And it's giving you 0.5 CO all over KO, or CO all over what? 2 what? KO. Remember, this O we are putting to this K is telling you we are talking about zero order O. Okay? And so, what does this tells you? What does it tells you? It's telling you that half-life of half-life of zero order reaction is dependent on initial concentration. That is, the higher the initial concentration, the higher the half-life. Is dependent on what? Initial concentration. Is dependent on initial concentration. So half-life is dependent on initial concentration. Please note this key point. Then, what do we mean by zero order reaction? A zero order reaction, the implication is that K, the R, the rate is equal to K raised to power of what? 0. That is total x plus 1 is 0. That means rate of zero order reaction, in zero order reaction, the rate of each reaction is equal to the rate constant, the each of the reactants or any of the reactants raised to power of 0, where the 0 is the overall order of that reaction, which is 0 we are talking about. In mathematics, anything raised to power of 0 is said to be what? 1. And so that means there is no concentration. This means that R is equal to K. R is equal to the rate constant. The rate of that reaction is equal to what? The rate constant. That means it is independent of initial concentration. Now, please note these two words. In terms of half-life, half-life of a zero order is dependent on initial concentration, whereas rate of a zero order is independent on initial concentration. Independent on what? Initial concentration. Rate is independent on initial concentration. Half-life is dependent on initial concentration. Please be able to differentiate these two. Okay? Then, in this zero order reaction, we can present it in terms of what? Graph. Watch. Look at the zero order reaction. That means the graph of concentration against time. And so it will have a negative slope. Graph of concentration against what? Time. Look at the against time. When you plot the graph of concentration against time, the slope will be equal to what? K. It's negative. It will give you a negative slope. That is why you see here negative slope. Now, the point at which it meets the concentration axis is what we call the initial concentration. So they can ask you to sketch a curve given concentration at a particular time and the time involved. And after plotting it, they will say deduce your initial what? Concentration. That means the point at which it meets your y-axis is your initial concentration. Okay? Please note this. Then for the shelf life means the time it will take the 10% of the initial concentration to get eliminated from the body. If we are talking about biological shelf life. Biological shelf life simply means the time it will take 10% of that what? Initial concentration to get eliminated, that is, get metabolized and excreted from the body. What do we mean? That's about biological. But about physical shelf life. Physical shelf life means the time it will take 10% of that initial concentration of that molecule or drug to be what? Eliminated from the body. What we mean by this is that shelf life is all about talking about expiry date. Yes, if they said a particular drug has expired, maybe it's to expire this month, so it has expired, right? And you check the drug. Let's say we are talking about vitamin C. That vitamin C, if they say it has expired, what it simply means is that 10% of its potency has been lost. That is about physical shelf life of vitamin C. So for physical shelf life of vitamin C, the implication is that 10% of its potency has been lost. That is 10% of the active ingredients in it has been lost. Yes. That means when you see someone after being told that this drug has expired, let's say vitamin C, and you see the person pick it and leak, don't blame that person. He has checked up something. He has checked if the physicochemical property of that drug has been affected. Let's say the color. If the color has not been affected, that is, the drug is stored in a good storage condition, that person might be tempted to take it and nothing will happen to him or her. The only thing is that it will only do 90% of the work, 10% will not be done. Yes, but it will not do any harm to that person. Yes, that is because the physicochemical property of that drug is not affected. But whether a drug has reached the expiry date or has not reached the expiry date, and you check the physicochemical property, let's say the color, it was white before and now it is now yellow or black, please run for your life. Don't take it, whether it has reached expiry date time or not. Let's say it has reached expiry date and the color changed from white to blue, red, yellow, black, any color that is no longer white, please never you take it. It means that it has reacted. The activation energy of that drug has been reached and reaction has taken place, so it is reacting already. Maybe produce a poisonous substance or product, and if it's a poisonous substance or product is produced, the implication is that it will be very harmful when you consume it. But if a particular drug has not reached expiry date and you bring it out, let's say it was white before and now it is yellow or black or any color, please don't say it has not reached expiry date so you will take it. Forget about what is written on it. Yes, forget about the expiry date written on it. The implication is that the storage condition where the drug was stored is not met. The storage condition the manufacturer asks you to store this drug is not met. Let's say it was asked to be stored in a cool, dry area and you left it in a hot area or condition. It will expire faster. Yes. Or maybe they say keep it is photosensitive, that you keep it away from light and you expose it to light. It will expire faster. And so, please, whether it has reached expiry date or has not reached and the physicochemical property of it has been lost, maybe start producing odor, color change, please do not consume it. So that is more of the things chemical kinetics is talking about, the half-life and the shelf life of it. Let's go back to what we are talking about. We said for the shelf life, it means that the CT is equal to 0.9 CO, because 10 has been lost, 10% has been lost, remaining 90%, and 90% means 90 over 100, that is 0.9 CO. Okay, and so you bring it to this zero order equation. 0.9 CO equals to CO minus KT 0.9. This KT 0.9 is telling you about the shelf life. This goes here. 0.9 CO minus CO equals to minus KT 0.9. Therefore, T 0.9 is equals to this minus this will be giving you minus 0.1 CO all over what? Minus K. There is 0. Now, the shelf life of a zero order reaction or the expiry date of a zero order can be calculated using this formula. T 0.9 equals to 0.1 times initial concentration all over the decay constant or the rate constant. This rate constant all over it. Every molecule, every substance have its decay constant. So you plug it here. So we have been able to get the formula for half-life of a what? Zero order reaction, the one of rate of a zero order reaction, and we said the half-life of a zero order reaction is dependent on the initial concentration and is gotten from 0.5 CO over KO or CO over 2 KO, whichever one you want. This KO is telling you zero order, the rate constant of a zero watt order. Then we also talk about the rate, and we said that rate simply means for that zero order, it means that the total x plus y is 0. That means anything raised by 0 is 1. The r is equal to the rate constant. And then the implication is that the rate of a zero order reaction is independent on the initial concentration. There is no initial concentration here. Okay? We also said that about shelf life, that is what we call biological shelf life, the time it will take 10% of that drug to get eliminated from the body. But when we talk about physical shelf life, we say the time it will take for 10% of that drug to get eliminated. Or for the physical shelf life, we say it is time it will take 10% of that potency of the drug to get lost. That is about physical shelf life. Okay? Now we also went ahead to see how to get it, that it means 10% has been lost, so 0.9 CO. I will be having CT will be replaced with 0.9 CO equal to CO minus K T09. So this minus, it will give you minus 0.1 CO. Then we divide it by what? Minus K, so that we'll get the value of what? The shelf life. So that is for this. Okay, we want to go to first order reaction. Please, if you do not understand a particular point or particular thing we just said, please make use of the comment box below and ask your question. If you do understand it and enjoy the topic, please feel free to click like button and share to your friends and your classmates at the end of the watching. Okay, let's go to first order. Under first order, we say that its equation is ln C equals to ln CO minus KT. That is for what? First order. Yes. Let's see some examples of reactions which obey first order. Think of radioactivity. Radioactivity is one of the reactions that obey first order. Yes. Now in first order, look at how the graph goes. The graph of what? Ln C against what? Time. And when you have a graph of ln C against time, here is negative, so it will give you a negative graph. A negative graph. And so look at it. A negative graph. Okay? And so what you do here is, you say the point at which you meet your y-axis is called ln CO. And the slope is called K. K1. That means once you finish plotting the graph, this point is called ln CO equal to what? X. Whatever you get here, you call it X. So ln CO equals to whatever you get. If they ask you to get your CO, you say CO equals to what? Exponential what? X. Exponential X. That is, remove this term, put what? Exponential, and put X. So that is how to get your what? Your CO when you finish plotting. So you just use your scientific calculator. Once you press shift lane, it has packaged it this way. You now put what you got as a value, what you got from here. That is what will give you the value for CO. Okay, thank you. And we go further to now discuss the half-life and shelf life of a zero order. But before then, what does the rate talk about? The rate talk about K2, K1, a raised to power of what? 1. That means for first order, the total s plus y will be 1. That means that the rate of a first order reaction R is dependent on what? Initial concentration. R is dependent on what? Initial concentration, CO. Yes, please note this. I've mentioned what you have to note here, because when we go into calculation or question solving, you will be able to note what we are talking about. Once you are done with this first order, we'll look into their units. Units of what? First order. Units of zero order. But we have seen that R is dependent on this. Let's go to their units. Units of order of reaction. Unit of order of reaction. Because if a question is asked and you do not know the formula you have to use, you can use the formula, you can deduce the formula you have to use from the unit. Okay, unit formula is equals to, we say concentration all over time times 1 all over concentration raised to power of what? N, where N is the order of reaction. Concentration, this concentration can be in mole per liter or mole per dm cube. So which one do we use? We use any one. Let's use mole per liter. This means mole for zero order, its unit is mole per liter divided by what? Time times mole per liter divided by time times 1 over conc raised to power of 0. Anything raised to power of 0 is 1. Why are we writing 0? Any means order of reaction, and order of reaction is 0. So anything raised to power of 0 is 1. 1 over 1 is 1. That will be giving me this to be mole per liter. Change this division to what? Times 1 over time. Now, what is the unit of time? The unit of time can be in second, in minute, in hour. Okay, let's say the time is in seconds. All over seconds. So we will be having it mole per liter per what? Second. When everything comes up. Then for first order, as we said in the starting point of the video, we will be concentrating on zero order, first order, second order. For first order, we say mole all over liter all over second. That is the time. Times what? 1 over conc raised to power of what? 1. Now, this is a concentration which we say is mole per liter, right? Yes. So we replace it with conc. Okay, this we cancel this. That will be giving me 1 over second or per second. So when a unit of K is constant, when a unit of this K is this, know that we are talking about zero order. When a unit of this K is this or this, know we are talking about first order. Then when a unit of K is for second order, we say that it is concentration all over second. Remember, we said that concentration is mole per liter or mole per dm cube, okay? Times 1 over conc raised to power of, what is your n? Any second order is 2. So this will take care of one of this. That will be giving you 1 over sec and conc, and 1 conc remaining. So what is the unit? The unit of it is, for the concentration, let's sort it out. For the concentration, we say concentration is what? Mole per what? Liter. Are you getting it? And so what will happen now is that this L will come up. L, then this remain down. L mole per what? Second. Okay. So we now say the answer is what? L per mole per second. That is the unit of second order. What are we trying to say now? In this zero order, mole is not having power of -1, but here mole is. So how you can memorize it is that zero order and second order interchanges their powers in mole and liter. Mole will turn to per mole, while per liter will turn to liter. That is about it. So whenever you see any of these units, be able to deduce which order it falls.